Alright, welcome back. In this, we're going to go over acid-catalyzed hydration and tautomerization Keto-Enol of Alkynes. I made a lifetime total of $526.90. This video is going to be painful, so we're going to take it extremely slow. And the reason it is painful is you'll actually see in a few slides. So what we're going to do, here's the overview. We're going to talk about what acid-catalyzed hydration is. We're going to talk about the recipe. And then you're going to begin to cry. Because this is the mechanism. It is awful. Really bad. So I would not blame you if I see little tears running from your eyes. But my goal is to turn those tears into tears of joy. So we're going to go over keto-enol and what that actually means and what it is. Then we're going to go over what internal alkynes and terminal alkynes and how they differ regarding acid-catalyzed hydration. Then we're going to go over a bunch of practice problems. Now, these practice problems, I designed them. We're going to go over it so that a complete fucking idiot would know how to do this. And I know you guys are really smart. The people that watch my videos are really smart. I know that. But what I mean by idiot, I mean people that would drive under the influence while texting their friends that vaccines cause autism while listening to a podcast about how the earth is flat. I don't know. That's how bad. But I know you guys are nowhere near that, so you're going to be geniuses. You're going to know how you're going to know how to do this very easily. You're going to be able to figure out very quickly. So, recall that alkenes can undergo acid-catalyzed hydration. So we would have an alkene and we use hydronium or H2SO4, sulfuric acid, and water, which would turn into hydronium. And then what we're doing is we're adding water. But how we're adding water is adding an OH group and a hydrogen. So remember that H plus OH would be H2O, and that's why it's called acid-catalyzed hydration. We're not directly adding a molecule of water, we're adding it into parts. One is going to be OH and one's going to be hydrogen. Now, alkynes can undergo acid-catalyzed hydration, but it is very complicated. The reason is because the mechanism that involves alkynes, if you were to use this, is very slow due to the triple bond. So chemists found a way to do the reaction with these reagents, but something else interesting happens, where you get an enol and a ketone. So we have successfully actually added our OH and hydrogen, but the consequence is forming an enol and a ketone, and that's what we're going to go over. So here's the recipe. We need an alkyne. We're going to need sulfuric acid and water. Now, the key is that sulfuric acid doesn't do anything. I talked about this during the acid-catalyzed video of alkenes, that when you combine sulfuric acid and water, we actually create hydronium. Water gets protonated in the form when in contact with a strong acid like sulfuric acid. Because strong acids want to give up protons, so sulfuric acid wants to give up its proton, and that proton's going to go to water, and it's going to create hydronium, and that's the main player. We're also going to use mercuric sulfate, and you will see why momentarily. Now, what we're going to do is we're going to do a mini oxymercuration-demercuration reaction. Hopefully you remember that when we talked about alkenes. So, hopefully you see mercury and you're like, okay, oxymercuration-demercuration. Here's the mechanism. The first two sections are about acid-catalyzed, and the last section here is about tautomerization. So let's go over it. We have our alkyne. The pi bond is going to attack the ion of mercury. The sulfate part of it does not do anything. It's just to stabilize it because mercury itself has a positive 2 charge, which is not stable. We cannot have positive charges roaming around in solution. We need to stabilize it somehow. And that's why we bond it with SO4, sulfate. So the sulfate doesn't do anything. It's this we care about. So the pi bond is going to attack this because this is positively charged. This is like electrophile. 2 plus. It's positively charged. So acts as electrophile. So it's going to bond to the less substituted carbon because we form our carbocation, and the carbocation needs to be at the more substituted carbon for stability purposes. So once again, this is the less substituted side, this is the more substituted side. So that is why the mercury ion bonds here to the less substituted side, so we can get the carbocation on the more substituted side. Now what's immediately going to happen is the electrons are going to attack the carbocation. So let me draw that in actually. We create this bridge-like structure here, this pyramid triangle-like structure, exactly like oxymercuration, demercuration. This stabilizes our alkene. Now the thing is, it bounces between these two things. When it actually turns into this form, we can actually move on. Water, which is from our solution, is going to do a nucleophilic attack to this positive carbocation. So remember, I told you it's in this form. So when we get to this stage, so it bounces between these two things, but once equilibrium favors this side, that's when we can continue, when we have a carbocation. The water is going to act as a nucleophile. It's going to attack the carbocation. So the water is going to bond. It's going to join to this more substituted carbon. Water is joined, but look at this. Whenever we do a nucleophilic attack, our nucleophile always gets a positive charge, which is bad. We can never have our nucleophile have a positive charge, so we must fix it immediately. So there's more water in the solution. It's going to deprotonate it. And this bond is going to dissociate into electrons and give it to oxygen to stabilize it. Now we have our OH group. We have successfully added our OH. Now we just need to add the hydrogen for acid-catalyzed hydration. Because remember, I said acid-catalyzed hydration, we're adding water in the form of OH plus an H. So we have covered this part. We're halfway done, kind of. But we still have this mercury ion that is attached. We don't want it there. We have to do something about it. We have our alkene here. This is going to attack hydronium. And remember, hydronium is coming from this solution. When water and sulfuric acid combine, this is both in the beaker, when they both interact with each other, we get hydronium, and now it's its turn to participate in the reaction. Water had its opportunity, it did its thing, now it's time for hydronium. Because you got to think about, not all the water has turned into hydronium in the beaker. There is some left over. That's why we started off with water, and now the water has been used up, and now we can go to the hydronium. Okay. The pi bond of the alkene that we have is going to attack the proton and steal it of hydronium. That is what we did. So remember, we have now sacrificed a pi bond. The water, when every time we sacrifice a pi bond, either when it's from an alkyne or an alkene, we always get a positive charge. The positive charge must always go to the more substituted carbon. We have sacrificed the alkene by adding a proton, a hydrogen, I should say. We have now successfully added our hydrogen to this molecule. The hydrogen's right here. So we have successfully completed, well, have done the acid catalyzed portion. We have now got our water, our hydration. We now have OH plus H. Once again, the H is now here. And the reason we do this, it goes to the less substituted side so we can get the carbocation on the more substituted side. This has more branches than this. We have a carbocation. We need some way to stabilize it. So the electrons, the free electrons from oxygen, the one pair, is going to go to this bond and create a double bond. Like so. This is our, there's an equilibrium here. Transition state. Now what's going to happen? is that mercury ion sees it has the ability to leave. It has the opportunity to leave. So it will do so. This bond will go away and turn into a double bond. Now, since we have a double bond here, it is illegal to have a double bond right next to it, like this. So the pi bond from this is going to go and give its electrons to oxygen and stabilize the positive charge it has. So mercury has left, and we get this. This is called an enol. The reason it is called enol is because, remember, alkenes, let me actually spell it out for you. Alkenes have the suffix en. That's where the en and enol is coming from. Ol means alcohol. We have an alcohol and an alkene, or an alkene ene, and alcohol ol, an enol. The alkene is always adjacent to the alcohol. It is not part of the alcohol, it is adjacent to it, right next door. It is part of the carbon that bonds the alcohol and this pi bond here, alkene. Okay, we have our enol. The problem is that enols don't ever stay as enols. And I'll explain why in the next slide, why this is the case. What will happen immediately is we have hydronium still in the beaker. We have not used all of it. There's a lot of it in there. The pi bond is going to attack the hydronium. It's going to get protonated. So we have sacrificed our alkene. And remember I said earlier, whenever we sacrifice an alkene, we always get our carbocation. And the carbocation is always on the more substituted carbon. What we have done is added the hydrogen to the less substituted carbon. It'll go right here. That's what we do. So, pi bond's gone. Goes away, bye-bye. We have our carbocation. The hydrogen has gone here. It's there, it's invisible. Well, we need somewhere to stabilize the carbocation, so the free electrons on oxygen are going to go and stabilize it by creating a pi bond, a double bond. It is exactly, literally, like this. The step from the top. It's literally this. We're just doing it again. Now, what's going to happen is instead of the mercury leaving like how we did before, it's going to be the hydrogen that is part of the alcohol that's going to leave. And it's going to give its electrons to oxygen to stabilize the positive charge. Now, how the hydrogen leaves is due to water. Water's going to steal it. Because we still have water in the beaker. It still exists. Now, the reason, I should say, okay, let me go back. The reason water exists is because we made water here. When we use the pi bond to steal the proton, one proton away from hydronium makes water. That's where the water is coming from. That's why it's still in the beaker. So water's going to go and steal it. It's going to steal the hydrogen away, and the electrons are going to go to the oxygen. When this happens, we created a ketone. The hydrogen right here is still there in that position. So we went from an enol to a ketone. This is why it's called enol keto, or keto-enol. Okay, that was a mechanism. So the main point is this part, and you will be asked this a lot in the future, especially in organic chemistry 2. If you do organic chemistry 3, you'll also need to know this. And if you take biochemistry, this is a very big component of biochemistry. I swear to God, tattoo this on your arm or something, because it is that important. Okay, Ketoenol. So under acidic conditions, which is actually necessary for hydration reactions to actually occur, because in order to add the hydrogen, it needs to be in acidic conditions, because we're using hydronium to add the water. Hydronium itself is acidic, so we are in acidic conditions. This is in the beaker, which is in hydronium is very acidic. These two stuff are in the beaker, so we're always in acidic conditions to actually do the hydration reaction. The enol immediately turns into a ketone. We're in acidic conditions here. This is hydronium. This is all in a beaker. We have the enol. That is why we get the ketone. It pushes all the way to the ketone. So this is what keto-enol is. And this is called tautomers. Tautomers are constitutional isomers. That means they have the same molecular formula, but they change structure just based on the migration of one proton. We are moving this proton here. They're switching places. And that's what tautomers are. It's constitutional isomers, same molecular formula, just different structure due to the migration of just one proton, one hydrogen. You'll also notice the equilibrium lies for the ketone. This is always usually the case. The reason this is because even a little bit of acid, even the trace amount of acid or base will push it towards the ketone. Now, when you do this reaction in real life, in an organic chemistry lab, you have beakers. The beakers are usually used up. They've been used prior and before. Even if you wash them, you could scrub them and scrub them and scrub them after a reaction. There will still be traces of acid or base. And that is why when you do this reaction, it always favors the ketone because, we're in acidic conditions most of the time, and it will favor the ketone. In order to have this at complete equilibrium, you would need fresh beakers, like completely fresh beakers that have never been used. And even then, it's almost impossible to reach equilibrium. So whenever you do the mechanism, the reaction, and you're asked this on an exam or practice problems, you should always put the ketone as your answer unless stated otherwise. Oh my god. Okay. Now, let's talk about internal alkynes and terminal alkynes because the reaction can happen with both. Let me talk about internal alkynes. When you do the reaction, what will happen is if the alkynes are not symmetrical, you can see that they're not symmetrical because I have an R here and an R with an apostrophe. This is telling you that they're two different R groups. They look different. They are not symmetrical. When this happens, you get two products, two ketones, and you're going to get two enols. This is pretty much useless because you cannot control what product you want. Say if you just wanted this product and only that product. Well, you can't because you're going to get this one as well. So it's a problem. Now, when the internal alkyne is symmetrical, then you're only going to get one answer, and that's completely fine. If you don't understand this, we'll go over in the practice problems. Don't worry. Now, here's a trick with drawing internal alkynes. Whenever you have an internal alkyne and you have your molecule, your compound, whatnot, 4 carbons are going to be in a straight line. 2 of them are going to come from the alkyne itself, and the neighboring ones are going to be in straight linear fashion. That is the trick to drawing these, and you'll see exactly what I mean in the practice problems. If you don't understand this, you will see. Now, terminal alkynes, when you do the problem, you're just going to get one answer, which is great. Great for us. It makes it easy. Now, when you draw terminal alkynes, you'll notice that they're always in a 3-carbon straight line fashion. This is carbon 1, this is 2, this is 3. So these 3 carbons are going to look straight to you. So when you draw the molecule, they should be straight, linear. And this is not a carbon, right? This is hydrogen. So technically the molecule cuts off here. That's what it would look like. You'll see exactly what I mean very shortly. Oh wait, tell me the keto-enol products of the following reactions. Here's the shortcut. Very, very, very easy. I want you to show me the enol and the ketone. So both products. Let's do the enol first. The trick is you're going to have to put an OH at the more substituted carbon. That's half the job done. You have done it. If you can realize what the less substituted carbon is and more substituted carbon is, you're home free, basically. You're done. The OH group is going to go with the more substituted carbon. Here. What you're trying to do is you're going to try to form an L shape when you're doing it with terminal alkynes. This is a terminal alkyne. As you can see, the reason we know this is a terminal alkyne is because there's no R group here, but also, like I said, we have 3 carbons that are in a straight line. 1, 2, 3. So we know it's a terminal alkyne. That means we know we're only going to get one product. Okay. We need to form an L shape. And what I mean by L shape is the OH group is going to point up, or it can point down depending on the orientation of the molecule. And the alkene that you do, because you're sacrificing a double bond, you're sacrificing a pi bond. So we lose a pi bond. That goes bye-bye. We will now add an OH group, like that. Now we have to make this geometrically look good. This does not look good, right? This looks ugly. The way you do this is to kind of make an L shape. So you're just going to shift this like that. So we kind of got an L shape like this, a little bit. And that is literally your answer for the enol. You're halfway done. Very easy now. How do you get the ketone? All you need to do is erase the hydrogen, erase one pi bond, make it look nice, and now make it a carbonyl. Make it a double bond here. And make it a little bit, okay, you make it look a little nice here. And that's our ketone. That's how you do it. That's the answer. So we just did, okay, this is our enol, which does not form, really. It doesn't stay like this. Very quickly turns into this. We just did the entire mechanism that quickly, that fast. I'll make a video on the actual mechanism probably tomorrow. But yeah, that's it. Okay, let's do B. Same reagent, same stuff. We have a terminal alkyne. How do I know this? We have 3 carbons in a row in a linear looking fashion. 1, 2, 3. This is a terminal alkyne. That means we're going to get one answer, one enol and one ketone. The OH group must go at the more substituted carbon of the alkyne. This is more substituted than this one. So we already know the OH is going to go into here. So now we have to make it look nice. The OH group is going to point up because we're at an uphill slope here. That's one of the other tricks. So OH is going to point up. So let me just delete this. We delete one pi bond. Get our OH. And now we have to make that L shape. So you have to fix it up a little bit. Good enough. We have an L shape. And that is our enol. Now to get the ketone, once again, do a lot of erasing. Erase your hydrogen, erase your pi bond. Put the double one now here. So change the position of the double bond and move this to make it look nice. And that is your answer. That's your ketone. Ta-da! Okay. Oh, C. Okay, now we have an internal alkyne. How do I know this? You'll see that we have 1, 2, 3, 4 carbons that are linear fashion in a straight line. So this is our key that we indeed have an internal alkyne and that this is not symmetrical. The R groups are not equal. So we're going to have two answers. Like I said, two answers. Here's the trick. Let's do one of them. You're going to do the exact same thing we've been doing, but we're going to do it twice. What I mean by that is the OH group is going to come here. That's going to be one answer, and then we're going to have our ketone come from here. And then the other answer is going to come from here. So let me show you. Let me do this one first. All right, erase this. You'll notice that this does not look correct, right? This looks a little strange. So you have to redraw this so it's in a zigzag fashion. So whenever you have an internal alkene, we have to kind of make it in a zigzag fashion. How many carbons do we have? 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. Yeah, okay, that's good. And now our double bond, our alkyne here, 1, 2, 3, 4, 5. Carbon 5 and carbon 6. 1, 2, 3, 4, 5. Okay, now we have an alkene instead. Perfect. Let's actually do, let's just make it easy. Let me do this carbon first. Okay, we have now our alkene. Now what do we do? Well, OH. Ta-da! That's it. OH. Because we just did the alkene, right? We just made the alkene. That just leaves the OH group on them. And then don't worry about the more substituted or less substituted carbon part. Because you have to make both of them. So it does not really matter. Okay, now we have our OH. This is our enol. To get the ketone, what do we do? Same thing as before. Erase the hydrogen. Erase the pi bond. Put the double bond now here. And make this look nice. And that is our first pathway. Now let's do the second pathway, the second answer. Now we have to do it for this carbon here. So we'll do exactly that. That's our enol. Because we already we added the alkene already. So we just have to add the alcohol. And now to get the ketone, erase, erase, add, organize, done. There we go. That's C. Here's the answers. Okay, hold on. Calm down. Okay, there we go. That's our answers. Not too bad, right? Tell me the alkyne for the following acid-catalyzed reaction. Okay. The trick first is to figure out, do you have an internal alkyne that we're going to be creating, or do we have a terminal alkyne? Here's the trick. If you are one carbon away from the end of the molecule, this is the end of the molecule, you're one carbon away. So your ketone or enol is one carbon away from the black space here. Nothing. The end of the molecule, the end of the compound. You will make a terminal alkyne. If you are more than one carbon away, then you're going to make an internal alkyne. Okay, how do I do this? Well, like I just said, we're going to be making a terminal alkyne. And the way to make a terminal alkyne is the triple bond needs to go here. So that you're halfway done. Now you just got to redraw the molecule so you have 3 carbons in a row. Because I told you that terminal alkynes have 3 carbons in a linear looking fashion. So when you draw the molecule, you need to make sure you have 3 in a straight line and then draw the rest of the molecule exactly as it looks like. Like that. And then make sure you count your carbons to make sure you actually added the correct amount. You didn't leave enough or you didn't add it too much. So, just to prove it to you, we have 1, 2, 3 carbons in a row. And that's our terminal alkyne. Look at this doobie. What about this one? Okay, you can notice that we are not 1 carbon away from the end of the compound. We're 1, 2 away. Don't count this, but we're 1, 2 away. This is going to tell us that we have indeed an internal alkyne. Okay, now I told you internal alkynes, if they're not symmetrical, you will have 2 answers. If they are symmetrical, we will have 1 answer. Well, look at this. We only have 1 answer. There's only 1 answer. There's not a second molecule here. So we know that the alkyne that it starts from, our internal alkyne, must be symmetrical. And the way it is symmetrical is the alkyne, our 2 pi bonds that are going to be creating must be in the middle of the molecule. So we get rid of this. Now we have to draw this so we have 4 carbons in a row. So literally draw it so we would have 4 carbons in a row. Pretend. So we'll do like this. Okay, like that. 1, 2, 3, 4. We have 4 in a row. Perfect. And now just draw the rest of the molecule. And you'll notice it is symmetric. Like, I mean, my drawing's not the best, but it's symmetric. Ta-da! And that's the answer. And that's it. Hopefully you found this video helpful. I tried to make it as easy as possible. It is a complicated topic. But if you found this video helpful, please like and subscribe. Until next time, later.